I can tell from the attendance that a lot of people are watching at home, so hello everyone watching at home. But I'm glad everyone here came. I have a few announcements. Several people pointed out that we don't have a final schedule by the registrar. It's not our fault. We asked for one. But so we still have to schedule one. Sorry. So for all students, there exists a final. And we will make up some fancy method by which you can say, we'll propose a bunch of times in the finals week and see which ones you cannot make because of conflicts with other classes. Either by email or by web, we'll see how that works. We have some of the problem set ones graded, and they'll come back on your Friday recitation. And I want to reiterate the collaboration policy briefly because I think some people misunderstood a little bit. Everyone wrote down collaboration when they were supposed to, but what did they forget to do? The important thing is you have to write the solutions up yourself. Okay? You have to do your own write-ups. You can talk about the answers, you can discuss the answers, come up with answers together, but then you have to write it up separately. Don't copy. Okay? So that's clarify. And read the course information sheet again if that's not clear. Reminder, quiz 1 is coming soon, so study. So today I want to talk about order statistics, which is something completely new. Well, it's different from sorting, so hopefully that will please you. But it's related to sorting. So what's the problem? I give you n numbers, and I want you to find the ith smallest number in that list. Okay, so I is somewhere between 1 and n. So if you want to find the first smallest, that has another name of the list of numbers. It's the minimum, right? Okay, we'll start out easy. We'll get to harder questions later. If we want the last smallest, the nth smallest element, that's the maximum. And if I is roughly in the middle, so let's say it's floor or ceiling of n over 2, then that also has a name from statistics. You should all know it's called the median, right? Okay, so the median is particularly cool, but so that's maybe what you can have in the back of your mind. Finding the minimum and the maximum of n elements is pretty easy. Finding the median is trickier. But in general, we'll be able to find the ith smallest for any given value I. Okay, I want to give this a name. The ith smallest number I'll call the element with rank I. Okay, so the rank of an element is, if you sorted the numbers, then which position is it in? Is it in the first or the second or the third? Okay, but these n numbers we're given are not sorted initially. So that's what makes the problem interesting. So what's an algorithm for doing this? You should all have in mind some way to do this, not necessarily the best way, but all we've been talking about, or a lot of what we've been talking about in this course so far, gives you a natural approach to selection. Yeah. Sort it, and then take the ith element. Yeah, well, okay, that's definition of rank would be. So let's call that the naive algorithm. That's not very exciting. Sort the n numbers, and return the ith element. So A bracket I. And how long does that take? n log n. Right? So if we use merge sort or heap sort, the time is theta n log n to do the sorting. And then you have to look at the ith element. Well, that's just constant time. And that's a worst case bound as long as we're using a worst case n log n algorithm. OK, so yeah, that's n log n. The question is, can we do better? So I give you n elements not in sorted order. We know we could sort, and then it would run an n log n time. Can we do less than n log n time? Well, the whole lecture is about order statistics, so the answer is yes. But I'll leave a little bit suspense about how much better we can do. All right. Yeah, question? No, you can mess around with the list. That's not such a big deal because we'll allow you to make extra space. So you could make a copy of the list first and then mess it up. But yeah, we don't have to be in place. And you're allowed to change the initial list. So sorting is OK. Yeah. Good. So I'm going to give two more algorithms for solving this problem. The first one is randomized. And it's a divide and conquer algorithm. And in fact, they'll both be divide and conquer algorithms. So let me write the algorithm first, and then we'll draw a picture and see how it works. So it's called randomized select. And its goal is to find the ith smallest element in the subarray from P to Q. Because that will be useful for our recursion. There's never enough space on the board. I guess I could go down here, but it's not considered polite. All right. I'm going to anyway, sorry. Down to here. There's a bug in this. Good. It's the wrong time to find the bug, but, well, maybe I'll leave the bug for now, see if you can find it. I'll fix it in a moment. So let's draw a picture of what's going on here. So we have our array, and we're interested in the region from P to Q. So what the algorithm does is first it says, well, if I just have a length 1 array, P equals Q, well, then the I smallest element is the first element. I mean, there's only one element. So that's the base case. Otherwise, we do a random partition. So this is like in quicksort. Okay, you pick a random element, you swap it with the first, you call partition, and it rearranges everything smaller than that value and larger than that value. Okay, and random partition tells you, oh, actually, maybe it is correct. Sorry. Good. Random partition tells you the index of the partition element after it's been partitioned, A bracket R. So let's draw what's going on. You pick some element out that's now in position R. After you partition, everything here is less than A bracket R, and everything here is bigger than A bracket R. And this is our partition element. And R was chosen at random. And now K is the rank of A bracket R. So it's this length. So that there's a comment here on this line. K is the rank of A bracket R. Good, just the number of elements between here and here. And now what do? So now we want to recurse. We want to recurse on one of these two subproblems. So if you check, these two recursions are A from P to R minus 1, that's this first part, or A from R plus 1 to Q, that's the second part. Okay, first, there's a simple case where it could be that the place that we partitioned is exactly the element we want. Okay, it's chosen randomly, so with probability 1 over n, we get that, and we're lucky. So that's this case, I equals K. Right, K is the rank of A bracket R. We know that because there are this many elements less than it, and the rest are bigger. So if it happens that this is the rank we're looking for, we're done. So that's cool. Then you just return the partition element. Otherwise, the element we're interested in has rank either smaller than R or larger than R. And then we just recurse in the two parts. If the rank we're looking for, I, is smaller than the rank of R, K, then we go to the left part. It's got to be in here. If we're looking for the min, it's got to be in here, for example. If we're looking for the max, it's got to be over here. Any rank bigger than this rank, we go to the right subproblem. And that's what these are doing. Now, we also have to say what rank are we looking for. And if we go in the left subproblem, we want the same rank. If you're looking for the second smallest element, and you go over into this subproblem, you're still looking for the second smallest element. And what changes, so this is the same value of I. What changes is if we go to the right subproblem, because then we've chopped off these initial K elements. And we don't need to consider those anymore. So if we were looking for the K plus first smallest element, we know it's going to be the min of this array. So if it's K plus, if I is K plus 1, we should subtract off K, then we'll get 1, and that means we should get the min. Okay, just as an example. So in general, you just subtract off K, and that's which element you should look for in the right subpart. Let's do a little example here. So let's say we're given this array of 8 numbers. we want to find the 7th smallest. So I equals 7. And let's suppose that our random partition chooses element 6 as the partition. Oh, I'm going to use this as a cheat sheet here. And now you think very fast, you apply partition, and magically you can check, you'll get the following. So the crucial thing is that everything less than 6 is on the left of 6, and everything bigger than 6 is on the right of 6. But you have to run through the algorithm to check that that's really the order of those elements that it gives. OK, so what's k in this picture? 4, right? It's just the number of elements between 2 and 6. And we're looking for the 7th smallest element, which is bigger than 4. So we should go in the right half. So we're recursing here. And we'll recursively select which element? The 3rd smallest, right? We take what we want minus what we already have, what we're throwing away. OK. Good. And you can check what we're looking for is the 7th smallest. That's the next to largest, because there's 8 numbers. That should be 11. And here, we're also looking for the next to smallest element. And that should also be 11. So that will give the right answer. I won't do the whole algorithm because it's equally exciting. Good. So now the question is, how fast is this algorithm? We already have an n log n algorithm. We'd like one that goes faster. So let's first get some intuition before we get the analysis. This is a randomized algorithm, so we're probably going to do an expected time analysis. But let's first try some examples. And throughout today, I'm going to assume that the elements are all distinct, like part of last class. This algorithm will work in general, but the analysis is a lot easier in this case. OK, so let's get to some more interesting questions. What would be a good situation here? What would be a lucky situation? What's a good partition element? I mean, this is where all the choice is, and it's random. Sorry, it would be, you got it on the first try. That would be really, really lucky. To use earlier terminology, really, really lucky is you get it on the first try. Wow. So how long does the algorithm take then? Theta n, yeah. So you can check each iteration of this algorithm is going to take linear time. Right, you choose a random partition element and partition. It takes linear time. This is all constant stuff. Then you recurse. Okay, so the only real work here is this step. And so all of this is taking order however many elements you're dealing with, q minus p plus 1. So if you get it in the first try, great, linear time. Okay, that's really, really lucky. What's not quite so lucky, but still good. So now you have to start thinking about what the recurrence would be. If you're not really, really lucky, then you have to recurse. You split the problem. Yeah? If it were in the middle, yeah. That would do just dandy, because each time you're recursing, you cut the problem in half. And then you get a geometric series, right? If you add up linear-sized things that are halving at each step, it's dominated by the lead term, which is linear. Good. So even more general is, suppose I don't split it in half, but I at least get some constant fraction. It doesn't have to be right in the middle. It could be a third of the way, or 9/10 of the way. Okay, if the place where I cut happens to have rank 1/10 n, so n is the size of the array here, then great, I can throw away 1/10 of the element. There are 9/10 left, so that's the recurrence. And at each step, I have to do linear time. So we get to use the master theorem. Isn't that exciting? So the master theorem, we want to evaluate n to the log base b of a. What is that in this case, in this example? There's the thing, oh, gee, b is supposed to be n divided by b. I mean, it's more intuitive, right? This is how many times do I have to take 9/10 before I get down to a constant? This constant, I mean, here it's 1. So, sorry, 0? Oh, good. You even computed out, right? It's log of 1. Oh, boy. And the base here is the reciprocal of that term. So 10/9 of 1. Goes n to the 0. It's 1. So which case are we in? To compare f to the log, n to the log base b of a. Third case. Good. You remember which is which. And so what's the answer here? Linear. Just like I said it would be. OK, so that's cool. So that's a pretty lucky case, but you would expect that to happen a lot of the time. You're not going to cut right in the middle very often, but you'll probably cut somewhere in the middle half pretty often. Like with probability a half, you'll cut somewhere in the middle half and leave at least a quarter on either side. So that's looking good. What would be a bad case? So let me go back here. So where's a bad place to split? At the end, right. If I don't cut any elements off, I'm not going to do so well. So what's the recurrence for this situation? If whenever I partition, I happen to hit the first element or the last element, like the minimum element or the maximum element. In the worst case, so these are all worst case running times. The worst case is I don't get this. I have to recurse on a problem of size t of n minus 1, right? Plus, there's a linear term, because at each step I need to spend linear work. So the worst thing is I only reduce the problem by an additive 1. I get to chop off one element. That's it. So what's the solution to this recurrence? N log n? N squared? Which is right. Let's take a vote. N log n? N squared? Good. Democracy wins. It's n squared. Why is it n squared? It's a sum of arithmetic series, right. This is an arithmetic series. sum of I for I equals 1 to n. So that's n squared. Well, actually, that's really, really bad, right? If we sort, we can do it in n log n time. So, gee, the worst case running time of this randomized algorithm is n squared. That's a lot worse than the algorithm we already know. The good thing is, here we were really, really unlucky. I mean, this might happen once, but it's not going to happen every time. That happens with really low probability, exponentially low probability. So, let's prove that. So this is the analysis of the expected time. Now, this analysis, you've seen one expected time analysis in lecture. That's for quicksort. And this will be very similar to the quicksort proof because we're doing very similar things, right? We do a random partition of the elements, and then we recurse. Now, with quicksort, you had to recurse in both parts. Here, we just recurse in one part. Okay, but we're still using this random partition idea. So the proof will look similar, but it'll be a little simpler. And, OK, it'll be a little simpler. Good. So a lot of this will be review. So if you forgot the quicksort proof, then you get to see it again, which is good. So let's say, what's a good wording for this? Let t of n be a random variable which represents the running time of the algorithm on n inputs. And just like in the quicksort proof, we assume that all the random numbers that we generate are independently chosen. OK, so each time you call a random partition, it picks a different random number. And again, we'll see why that's important. Now we want some indicator random variables. I think I don't need this algorithm anymore. OK, you remember each step costs linear time. OK, now we set up some indicator random variables, which tell us which split got made at a particular recursive call. So x sub k will tell us whether we got a k-way split, or sorry, a split where one side has size k. So if it's a k on one side, that means there's n minus k on the other side minus the partition element. Okay, so x sub k will be 1 if that's the case, and 0 otherwise. Good. So let's do a little bit more setup. Now, all we want here is an upper bound. Right, so we want the worst case running time. If we split, let's suppose that x sub k equals 1 for a particular value k. We split into k on the left side, n minus k minus 1 on the right side. Now we have to recurse on one of those two subproblems. So which of those is the worst subproblem? The bigger one, whichever is bigger. So it depends on the value of k. But to get the worst case running time, we can assume that the algorithm recurses in whichever is the larger half. Okay, so now we get a recurrence for the running time. Let's go here. Oof. Okay, I'm not going to do that. It's stuck. Is there... Ah. Okay, I won't admit exactly how weak I am. I just erased what got put up. Good. Oh well. Okay, now we want some recurrence for t of n. And one easy way to write that is as a big case statement, depending on which x sub k is the case. So it could be that x sub 1 equals 1. Am I going to have enough space there? Probably not. So you'll need to leave about 30 characters worth. And then here we'll have, well, what's the recurrence? So if we split 1 versus n minus 1 minus 1, then the recurrence is t of n equals. So t of 1 plus t of n minus 2. T of n minus 2, right. Because probably n minus 2 is bigger than 1. So we assume we only recurse on one of the two subproblems. We assume that we recurse on the larger one. So in general, we can write that as a max, just so that it will generalize easier. Max of 1 and n minus 2. And then, as you say, there's a linear term at the end for each step. And if x sub 2 equals 1, you get the same thing. But now you split either to a size 2 array or into a size n minus 3 array. And at some point, and initially this is the larger term, but at some point it will switch the other way around. Because at the end, right, we get x sub n equals 1. And then it's a max. Now the left part contains, I guess you can't actually get all the way to n, right? Because then you'd have, start at 0. Good point. Because you may have no elements in the left half. All right, let me rewrite this, sorry. You can put them in a different order if you want, but I want to put them in the right order here. 1, 2, 0, 1. So here there's 0 in the left half. Good. 1 in the left half. The max there could be in the left half is n minus 1. Because there's always the one partition element, which you don't count on either side. Okay, so in the end, the left half is bigger, but it just splits in the middle. Okay, so we can write this in general. So this is just like quicksort, right? We can combine all of these terms. Instead of having a big case, we can have a sum. Good. So it's sum from k equals 0 to n minus 1 of x sub k, the indicator random variable, times the recursive part, which is max of k on the left half and n minus k minus 1 on the right half. Plus order n. And I guess all of this is in parentheses if we want to follow exactly this picture. Okay? Now I leave it to you. You've seen the quicksort proof. This is the right setup. Now what do we do? We have this random variable t of n. We have this sort of recurrence for it. How do we find what we're interested in? Sorry? Take expectations. Right? Because we want to know we don't care what t of n is. That's a random variable. We can't write down that and accept it as a recurrence. We want to know the expected value of t of n. So let's take expectations of both sides. So I'll just do what you say. Think about what the next step is. So what do we do now? Sorry? Linearity of expectation, right. So this is an expectation of a sum, so we can split out the e's. Okay, so we can put this e inside the sum. This is also a summation of terms, so we can split that out. Okay, this is not a very exciting expectation. What's this? Is that? Oh. What did I do wrong? Forgot the xk, right? This xk, this parenthesis was in the wrong place. Right? Xk multiplies everything, because I only get one linear term. I don't get one for every possible case. So this should be a slightly more interesting expectation, which is e of xk times theta of n. Thank you. This parenthesis was also in the right place, so please change your notes to go there. Xk multiplies by that whole term. Good. I'm missing some end brackets. Okay? Stop me if I make any mistakes. So what should we do now? I mean, let's look at the left term first. That's where the more interesting thing is happening. You have an idea? Or? You've answered all the questions, so sorry. Got to get more people answering. You've seen this sort of proof before. It's almost the same. What was it? In quicksort, this was you had to recurse on t of k, and you had to recurse on t of n minus k minus 1. So it was a sum of two t terms. Here we just have t of n max. So it's almost the same. If you can remember all the way back to the quicksort proof about a week ago, any ideas? What do we know here? Well, let's do the right term. Maybe that's easier. Any ideas? Yeah. The left term is 3/4 n. Can you fill in steps in between there? That was a little fast.
K goes from 0 to n minus 1. The first half, the maximum decreases steadily from n to n halves, and then increases steadily thereafter. And then intuitively, that will produce 3n going forward. You can evaluate out kind of what the central integral of that region.
Right, so the picture you're imagining is, let's take k, this is k from 0 to n minus 1. And you claim here, well, the max is big, then it goes down steadily, then it goes back up steadily, and this is like n over 2. This is n. Yeah, so those are the things we're summing up, and we want to if you pretend this is an integral, we want to figure out this area. But, I mean, there's expectations in here, so it's not quite that simple. There's the x sub k. There's t's even. Don't forget the t. If you're just adding up this, that's right. I mean, if you get the, you have to take this area and then divide by the probabilities as well to get the expectation right. All right, go ahead. Split the expectation into a product, right. Let's do that. What's the expectation of theta n? Theta n. Good. Why can we do this? Independence, right? That's when you can take the product of probabilities or of expectations. So we're using the independence of x sub k versus everything in here. So this is a recursive call. It also makes random choices, but because all those random choices are different, any indicator random variables that we get recursively in here are independent from this one because it talks about a different random number. Okay? It's like quicksort. Over here, we're using the expectation between a random variable and a non-random variable. That's always true. Okay, but this is from independence. What's this? Oh, I shouldn't erase. Remember what xk is. Sorry. xk, you get a k to n minus k minus 1 split. So what's the expectation of x sub k? This is either too easy or you've forgotten. This is an indicator random variable. What's the expectation of an indicator random variable? It's probability. So what's the probability that we get a k to n minus k minus 1 split? 1 over n, right. They're all equally likely. There are n possibilities from 0 to n minus 1. Okay, so now we get to evaluate this. The 1 over n can come out of the summation. So we get E t max k n minus k minus 1. Plus, now what's this over here? This is also 1 over n. So what's the sum? Theta n. Right? You take 1 over n times something, and then you multiply it by n. You get the original something. So it's just a theta n. And that makes sense, right? You get theta n in all cases, so it shouldn't matter what x sub k is. Okay. That's as far as I want to go. Once I get all my brackets matched. This is now a recurrence, right? We have e of t of n, that's what we started with, equals this. Or it's actually at most this. Right? Because we were always assuming we went down the worst path, the larger of the two subproblems. So if you want to be precise, this is less than or equal to. And this is less than or equal to. Okay, but if you want to think of it as recurrence, you can just say that's equal, and this is the worst case running time in expectation. So it's worst case in which way you go, but it's expectation in how you split. Okay, so there's two things going on. Now we want to solve this. But can we simplify it any further, maybe, first? Forgot one step before we solve it. It's what you were saying about this max term looks like this picture. I'm a geometer, so what nice geometric thing can you say about this picture? It's symmetric, right, about here. So what does that tell you about the summation? This is reflectionally symmetric. If I go here, I flip that over like that, which is hard to do with your hand. You get the same thing. What does that tell us about the summation? Yeah. It's twice half the summation, right? So half the summation, well, let's say the larger half. It doesn't matter. We'll start at the middle. So the middle, to be safe, let's start at n over 2 with a floor and go up to n minus 1. That's definitely at least half. So this will be at most what we have here. And now we take the expectation of t of the max of k and n minus k minus 1. But now we know we're in the larger half. And so the maximum is actually just k. N minus k will be smaller. Oh, that looks much prettier, doesn't it? I mean, this is a little messy, but this is clean. Now we have a serious, clear recurrence. Oh, times 2. Thank you. Right, I also have to add on the smaller half, the lower half of the summation. So this is all times 2. This is outside of the summation, right? So I don't have to multiply that by 2. Good. Now this looks a lot like the recurrence we got in quicksort. The difference is here we had a summation, right? T of k plus t of n minus k minus 1. But there we also had the sum of the same thing. So actually the difference, if you go back to your notes, is that the summation started at 0 with quicksort. That's the only difference. Now quicksort, so this is definitely smaller than the running time of quicksort because we have fewer terms. Quicksort took n log n time in expectation. So this is certainly at most n log n, which is good. The algorithm that sorts and then finds the ith element takes n log n time. So we'd like to do at least that good. And the cool thing is that it does better. And so we want to solve this. And we'll use the substitution method. So we need a guess how fast it goes. And the guess will be that it's linear. And we'll prove that by induction using the substitution method. And I can't move that up. And to do that, we need a fact. And OK, I'll cheat and look up the fact. So the fact is, if you take the same summation bounds from floor of n over 2 to n minus 1 of k, then you get at most 3/8 k. Okay? K squared. And it should be also n, because I'm summing up to n. Good. Okay, that's similar to what you did before, and this is left for you as an exercise, just like in quicksort. Prove that using the summation methods that is in the beginning of the text. Okay. Good. So now we induct. So the proof of the claim is we use induction. So we'll assume by induction that E of t of n, or let's say t of some other value k, is at most c times k for all k strictly less than n, and then we have to prove it for n. So now we have E of t of n. We use substitution, which means we plug in this recurrence here, and we use the induction hypothesis on the subproblems. Sorry, this is our recurrence. Okay, each of these k's is strictly smaller than n, so we can use this assumption that E of t of k is at most c times k. So we get that this is at most 2 over n in front, summation k equals floor of n over 2 to n minus 1 of c times k. The c is a constant by assumption, so it can go outside the summation. And then you're left with a sum, which we know from over here. And so we get this bound. So this is at most 2c over n times 3/8 n squared. Okay, you have to compute the constant out here. That the 2 cancels with this, leaving a 4. So this is 3/4 in total. And we'd like to, what do we want to prove? We want to prove that E of t of n is at most c times n. So let's write this expression as the desired value minus some residual. And the residual, it was 3/4 c. The n's cancel, so 3/4 c times n. So this should be 1/4 c times n. If I subtract off 1/4 from this, I get 3/4 c times n, right? And then there's the theta n term. And we want that this is at most c times n. And that'll be true so long as we choose c sufficiently large. Okay, why? This is some constant times n, and this is c over 4 times n. So if we just make c more than 4 times this constant, this thing will always be positive. Okay? So that c over 4 times n dominates the theta n term. Is there any other constraint on c? It's a memory test from the base case, right? There's also a base case in here, which is that E of t of n is a constant for n a constant. Okay? And then you have to know that E of t of n is at most c times n, even when n is a constant. That's the base of the induction. So that may also push up c. And that's the end. Any questions about that proof? So what did we learn? We learned that randomized selection, RAND-SELECT, runs in linear expected time. That's good. That's better than our n log n. And linear is the best you could hope to do. You have to look at all the elements. But it's not so good in the worst case. In the worst case, we know randomized select takes n squared time. And now we know in the expected case it only takes linear time. But if you're a theoretician, you want to know, can you guarantee that it takes linear time? And in some situations, like real-time programming, you really need an upper bound on the running time guaranteed. So you can't rely on the random numbers and the probability always carrying you through to linear. It'll usually happen. But if you want it always to happen, then we need another algorithm. Okay, because this could take n squared, which is a lot worse than sorting. Good. So what we'd like are these order statistics, finding the rank k element in linear time in the worst case without randomization. And this is another relatively old algorithm. It's from, where are we? From 73. And I'll mention the authors, because the authors are all very well-known people in algorithms. So this was a big result in 73. A lot of people were wondering how quickly you could do selection. It's a very nice algorithm. It's, for the most part, impractical, but it's very cool. So the randomized algorithm is very practical. It runs really fast if you want to find like the median. This will not run so fast in practice, but it will run in linear time guaranteed, which is cool. Let's see. These are all very cool people in algorithms. They've all done seminal work in algorithms and data structures other than this. Some of them you might know. So Ron Rivest is a professor here. He's the R in RSA. Okay, so he's taught this course several times. Von Pratt is one of the co-founders of Sun, way back when they started. So he's a zillionaire. He's been a professor at Stanford, but he just retired, and now he started up a company. Manuel Blum just moved to CMU. He's at Berkeley. Pink Floyd, no. Rob Floyd. He's also at Stanford, right? Tarjan is at Princeton, also working on a company. But, I mean, if you take any advanced algorithms courses, you will see all of these names several times. So I just thought I would mention them. So what's the algorithm? So this is just called select without rand. And I'll use notation that's a little less formal. So we'll get into more using English than writing down code that looks almost like C or whatever. So this will be more like English. And I'll also number the steps so I can refer to them later. I should say the algorithm will be similar to the randomized one. But we'll have one additional idea. Sorry, I'll just move this down a little. I have to cross it out, sorry. So the idea that we'll use is to, good, still have time. We need to generate a good pivot, guaranteed every time, if we want to get fast performance. So we're going to follow the same algorithm. We're going to pivot. We're going to partition. We're going to recurse on one of the two subproblems, just like before. But now we have to find a good pivot. Sort of the only thing you could imagine doing is recursing. So you can say, well, if I want to find a pivot that's roughly in the middle, I guess I should use partition. Right? That's sort of the problem. The tricky part is to make this run fast. Okay, so this is what we'll be doing. So here's the idea for generating the pivot. We'll divide our n elements into quintuples. Okay, write that a little nicer. Groups of 5, parties of 5, I guess, and find the median in each one. Okay, why don't I finish writing the algorithm before I give all the intuition. Here's where the recursion happens. Okay. This part is just the same as random select. Right? Once we find our pivot element x, which I'll describe in a moment, you check, well, did we hit it exactly right? So you return that pivot. Otherwise, you recurse in the left half or the right half, just like before. The new part is how we find this pivot x. And there are two parts. And let's draw a picture of what's going on with these two parts. You say, well, there are n elements. I can carve that into n over 5 groups, each of size 5. So if I want to just draw pictures of my elements, let's say as little circles, then I can group them in columns of 5. And then however many columns I have, well, that's n over 5, roughly. So let's suppose that's my collection of elements. I have 9 times 5 minus 1 elements. Nicely aligned in a grid. Okay. Be a little bit cleaner. When I write my notes, I write it on graph paper, so I don't get practice in this lining up. Okay, so there's 5 here. And the number of columns up to here is, didn't leave much room, floor of n over 5. Okay, and if I want to go all the way, that's ceiling of n over 5 to count this last row. But we basically won't care about the last column. Okay, we're only going to use floor of n over 5. Now the idea is, well, in each of these columns, in each of these groups, I'll find its median. There's only 5 elements. It's pretty easy to find it, the median of 5 elements. It takes constant time. Okay. In the notes, we like to say find the median by rote, because it's an easy repetition of things. Rote means other things. I looked it up this morning. It's kind of fun. Rote means the noise of the surf on the shore, in case you're curious. But it also means by memorization. But here it means by repetitive action. Okay? Gotta love the dictionaries in English. I think that's Scandinavian origin, but okay. So now we're going to find the median in each of these columns. So the way I'll draw that is with arrows. Do I want these pointing up or pointing down? It should be consistent with our notes, pointing up. So I'm going to say, well, let's reorder these so that this one, the white node, is the median. And these arrows mean comparisons. So this is the smaller guy, and this is the larger guy. Okay, so just think of this as a greater than sign. Okay, so that's how we draw that this is the median. And we do that in every one. And I won't draw all of them. I'll just draw a few. Okay, let's do this one too. Okay, so I do that for all n over 5 groups. And that's just going to take linear time, because each of these is constant time. Good. Now the second part is, well, now I have n over 5 medians, right? I have all of these colored circles. Well, colored white circles as opposed to colored black circles. Okay, I actually won't compute the median over here, sorry. So I'll leave that alone. I have all these numbers. There's n over 5 floor of them. Now I want to take their median. That's the second step. I find the median of those n over 5 guys recursively by selection. So I'm going to reorder the columns in the picture in your mind so that, let's say, this is the middle one. These guys are smaller. These guys are larger. Okay, maybe I'll use another color. So I want to draw in more arrows to say this guy is larger than all of these. Okay, I hope you brought your colored pens. Okay, that's clear. So now this is the median of the dark guys, of the white filled. And in your notes it's dark, hopefully. And now we can derive information, right? We have transitivity. So these are comparisons. This guy is smaller than this guy. But also this guy is smaller than that guy. That means this one is smaller than that one. Okay, so that's what this picture is for. We get to derive information from it. So what can we learn? I wish I could. Wow. Wrong part? It's this one? Yeah. Great. All right, I'm going to... That's right. You'd think. All right. All OK, so I'm going to say what I need to say about this, then I can erase it. Let's see. First step, how long does this take? We have to divide, find the median. I already said that took linear time. How about this step? How long does that take? T of n over 5, right? It's just a recursive call to this select algorithm of size n over 5 with a floor, but let's be sloppy and omit the floor. And now we have this recursion, and the recursion is, how should I write this? Say, as we did before. Okay, I didn't write it in my notes. Okay, we can say, well, this is T of k, or T of max of k and n minus k minus 1. Okay, we won't actually write that down explicitly again, but that's what's going on here, right? Again, you have the two recursive calls. The worst case, it's the max size. Okay. Why don't I put this theta n here so you don't forget that it's at step 1. Uh-oh. Now, we want to prove that this thing runs in linear time. It should be clear that it's correct, right? Because we're doing exactly what we did in the randomized pivot. Sorry, in the randomized selection. It's just that we're using a particular choice of the pivot, a deterministic choice of the pivot instead of a randomized choice. So it's definitely correct, just a question of how long it takes. We want to prove that it takes linear time. Good. And in 5 minutes. Okay, so we can do it in 5 minutes, no problem. What do we know? We know that this white guy, white colored circle, is bigger than these and smaller than these. Well, how many of those are there? Well, there's n over 5 total, and this guy fits roughly in the middle. Okay, so there's like n over 10 to the left. So we can write that. At least half of the group medians are less than or equal to x. Okay, again, I'm going to assume that all the elements are distinct, so I'll just say less than or equal to, same as less than. Okay, so the number of elements, as I said, is n over 5 groups, and then you divide by 2 and take the floor again. That's how many elements there are. Okay, but that's just floor of n over 10. Okay, you can check. So let's just say there's that many group medians less than or equal to x. Now we get to use transitivity. So I'm just counting what's going on in this picture. We know that these guys are less than this one. This is x. Should label it. Okay, we have n over 10 elements here that are all medians. Well, if they're medians, that means that they are larger than all of these. Right, so in fact, this whole rectangle, I mean, each of these guys is less than this one, and each of these is less than this one, each of these is less than this one. These three are all less than this one, so all of the guys in this rectangle are less than that white one. All right? So now we have to count. Oh, thank you. There's also these, because we have this equals x, and these elements are smaller than x. Okay? So when I say at least half, I was also including x, right, to get, because it may be in the middle. Good. Now what do we want? So we need to count those up. There's n over 10 here, floor of n over 10. And for each white element, there's 2 black elements above it that are smaller. Okay? So that means there are at least 3 times n over 10 elements less than or equal to x. Cool. And you can do the same thing for greater. For greater than this element x, you can look at this rectangle for all the group 5s, all the groups of 5s we have. Okay, all of these elements, if I drew in all the arrows, you'd see they all have to be greater than x. Okay, and you can do the same counting and there has to be at least 3 times floor of n over 10 elements greater than x. So that means we have a pretty good partition, right? There's 3/10 on the left and 3/10 on the right, at least. So if you draw the picture, 3/10 is somewhere here, and 10 minus 3 is 7/10 somewhere here. That means our partition is somewhere in there. That's our pivot, and there's this blank space at the end. Dealing with tenths is a little bit of a pain, so we can do a small simplification, and things will still work out. So we can say, well, if n is at least 50, then n over 10, how should I say it, is, sorry, 3n over 10. That's right. Get this right. I want to compare it to 1/4 n. So it's bigger or smaller? Sorry. Floors. All right. Got to do it all right. All right. I can't be sloppy. Charles won't let me be sloppy. Should I put a floor of n over 4? Doesn't matter. Good. This should be at least. Right? Good. Got it right. OK, so, well, 3n. So that means we can, instead of doing 3/10 and whatever, we can say, well, it's going to be even bigger than 1/4 and 3/4. OK, so that's cool. 3/4 and 1/4, I know where those are. Right? I know that my pivot will now be in the middle half, which is actually something I said early on, that would be a good choice if we could get in there. And now we know that we're in there. So, in fact, I analyzed this as a nice case, but let's write it in our remaining minute. OK. My eraser. So we get a recurrence, and in particular, I assume that n is at least 50 for this simplification. So for n at most 50, say, OK, that's our base case. It's constant. That's cool. That's the initial part of our recurrence. And then in general, right, we have one recursive subproblem. And now we know that its size, OK, there's the left half and there's the right half. And it's the worst of the two. So the worst place we could cut is right here. Then the left half has 1/4, the right half has 3/4. Okay, so the worst case, I want to write less than or equal to 3/4 n. Okay, now I don't have to worry about floors because I made this simplification, which is good. Plus, there's a linear term. And as we said before, this is, I guess, this is the master theorem. It's case 3, and so this is linear. Okay, this is the lucky case, not the really, really lucky case that we had in the beginning. I guess I was supposed to prove that by, sorry. This is wrong. What did I forget? Enough of the algorithm is still here. I forgot something. Yeah, step 2. Oops, sorry. That was too easy, wasn't it? It's not quite the really lucky case. In fact, there's t of n over 5 here, plus t of 3/4 n, plus theta n. Ooh, now I want to prove that that's linear. And I will do that with the substitution method. So let's claim it's at most c times n. And then we get t of n is at most c times n over 5 plus c times 3/4 n plus theta n. That doesn't sound good. Should I give that an explicit constant? No, it doesn't matter. Right. Good. So now I collect terms. I want to prove that this is at most c times n, so I'll write it desired minus residual. You add up the terms. 3/4 plus 1/5 is 19/20, right? You all know that? So we have to subtract off a 20th and the theta n. And the theta n is OK. I was a little worried. There's a c here, of course. The theta n is OK because I can choose c much larger than 20, and it will dominate this constant. Whew. OK. And that finishes the proof that t of n is linear. So this is a linear time worst case sorting algorithm. C has to be a little bit large, much bigger than 20 here. And if you don't do the simplification, I think it's much bigger than 10. Okay, we lost a factor of 2. Again, this is a really cool theoretical result, right? You can find the middle element in an unsorted list in linear time. It's also impractical. You'd use the randomized algorithm in practice. It'll run a lot faster, but still, this is a cool thing.